Last time we talked about standardized scores and the normal distribution. What I want to talk about today are three distributions that are quite distinct from one another. The first of these is the sample distribution, or the sample distribution. The second is the population distribution. And the third is the sampling distribution. Sampling. I've been up there in East Texas. Damn right. First of all, let's go back. We said at the very outset of this course that researchers seek to make statements about populations, observing that those populations are not necessarily all people in all places. They may be public school children between the ages of 5 and 8 taking history. Or they may be females who apply to graduate school. But regardless of the nature of the population, researchers seek to make statements about the population. But we also agree that typically accessing an entire population is, for one or another reason, simply impossible, or so outrageously expensive as to render it impossible. And so what the researcher is forced to do is select a subset of that population, a sample, observe or test the sample, and then make inferences about the population. What I want to deal with preliminarily is how a researcher goes about selecting that subset, how a researcher goes about sampling. And then we'll get to the issue of sample distributions, population distributions, and sampling distributions. The ideal way to sample is random sampling. The ideal way to sample is random sampling. You and I use the word random conversationally, and we use it to mean any of a variety of things. By chance, accidentally. In this context, that is in the context of sampling, random has none of those meanings, and random has a very specific meaning. Random sampling occurs when all subsets, random sampling occurs when all subsets of size n, as in Norman, have an equal probability of selection. Random sampling occurs when all subsets of size n have an equal probability of selection. That means that any subset of size 6 has the same probability of selection of any other subset of size 6. Any subset of 128 has the same probability of selection as any other subset of 128. What it devolves into is that every individual has the same probability of being selected. First of all, let me emphasize, random in this case has a very specific meaning. And that meaning is that in random sampling, all subsets of size n have an equal probability of selection. There are any number of studies that do not pursue this. In fact, almost no study uses pure random sampling. Because pure random sampling is an outrageously difficult task. Just as an example, in order to guarantee that all subsets have the same probability of selection, the researcher must specify every unit in the population. And because populations are unstable, that is extraordinarily difficult. What has evolved are two families of sampling procedures: the good family and the bad family. The good family of sampling procedures are called probability sampling procedures. Probability sampling procedures. These are useful because although they often violate the mandate of equal probability of selection, they do so minimally. Probability sampling is desirable because those procedures, although they may violate the mandate of equal probability of selection, they do so minimally. Non-probability sampling procedures violate that mandate substantially. Non-probability sampling procedures violate that mandate of equal probability of selection substantially. Let me just give you an example, a couple of examples of non-probability and therefore undesirable sampling procedures, because these are used commonly in research. One is to go through the telephone directory and contact every nth person, every 400th person, every 4th person, every 24th person, whatever it is. That violates the mandate of equal probability of selection, because before the sample is selected, I can tell you that the sample will include more people whose last name begins with the letter S than people whose last name begins with the letter Z. And if I can make those sorts of statements about a sample before it's drawn, before it's selected, it's an indication that this is a non-probability sample and therefore undesirable. Another undesirable another example of non-probability sampling is accidental sampling. Accidental sampling occurs when the researcher relies upon available groups. University undergraduates enrolled in Psych 1. The broad point here that I'm trying to develop for you is, first of all, there is the need for a researcher to select a subset of the population. Second, the most desirable way of doing that is to select that subset randomly, which means that all subsets of size n have an equal probability of selection. The third point is that typically is impossible, and what has evolved across time are two broad types of sampling. Probability sampling, which is desirable because those techniques violate the mandate of equal probability of selection but do so minimally, and non-probability sampling, and those techniques are undesirable because they violate that mandate in a profound way. If You and I walk through a shopping mall routinely. There are often people out there with clipboards, and they either come towards us or they don't. And when they come towards us, the best thing to do is turn your head away. Don't make eye contact. If you make eye contact, you're going to be sucked in. That is non-probability sampling. What the person has been instructed to do is look for a particular profile. And they approach people who exhibit that profile. The problem is not in that part of the study, necessarily. The problem accrues because there may well be a critical difference between people who agree to participate in a study and people who do not. Nonetheless, somehow researchers who want to talk about populations do so by selecting a subset of that population that is a sample. Observing the population, the sample rather, and then making inferences about the population. We can now talk about two sets of scores, or two distributions. One is the sample distribution, or the sample set of scores, and the other is the population distribution, or the population set of scores. Would you agree that the sample distribution is known to the researcher, and it is real? You've gone out and interviewed 42 people, or you've administered a questionnaire to 108 people. You have data. That data is real, and it's known to you. Yes? Would you agree that the population is real? That is, women between the ages of 28 and 41. That population is real. It exists in the outside world. Yes? Thank you. The population, however, is unknown to the researcher. The sample is both real and known. The population is real but unknown. Because the researcher has not interviewed or accessed the entire population. But the researcher knows that out there, in the real world, there is a population called women between the ages of 28 and 41. There is a population of males who took the GRE in 1998. Yes. So the population is real but unknown to the researcher. How does the researcher ever make statements about that population? You interview, I don't care whether you interview 25 people or have 25 people respond to a questionnaire or a set of questionnaires or a survey, or whether you have 2,942 people do that. How on earth does the researcher go from that sample, which is known and real, to the population which is real but unknown? Because this is the magic. Nobody cares, nobody in their right mind cares what 107 women between the ages of 28 and 41 have to say. Nobody in their right mind cares about what 2,042 males who took the GRE in 1999 have to say. What people care about and what they pay huge dollars for is information about the population. About all women between the ages of 28 and 41. About all males who took the GRE in 1999. So how do you get from that one thing that is known to you and useless to the thing that's unknown to you and of outrageous value?
Standard error?
That's part of it. That's part of it. The big idea, and that's one of the pieces. The big idea, the bridge that connects the sample scores, the sample distribution to the population distribution, is something called a sampling distribution. A sampling distribution. A sampling distribution is not real. It does not exist. It's hypothetical. But it's known to the researcher. Let's go back here for a moment and look at sample and population for a moment. There are things about the sample which we will know. We know that it has a mean, would you agree, of X bar. And it has a standard deviation of S. And we can, once the data is in hand, we can compute those scores. Would you agree? If we go out and have 25 people respond to an extroversion, a measure of extroversion, we will have 25 scores. And we could compute the mean and standard deviation of those 25 scores. We know, because we've used this terminology before, that the population has a mean of mu and a standard deviation. Where did it all go? I hit something. Oh God, I'm lost. I'm lost. Okay, we'll go back. I'll go back. Technology. Oh, I love it. I probably do need to scroll up, but I don't have the time here to learn how to scroll up. but believe me, I really do appreciate you telling me that. and I'm not being facetious. I appreciate you telling me that, and if you'd walk up here and do it for me, I'd say, okay, well done. As being left-handed, this whole world is against left-handed people. Well, the other left-handed people look at you as if you're a member of the in-group, but none of us like ourselves because we're left-handed. Oh, you see, this is what happens. When we have a sample set of scores with a mean of X bar and a standard deviation of S, and we can compute those. We have a population distribution which we know has a mean of mu and a standard deviation of sigma. And what we want to do is use X bar to estimate sigma and or S. Sorry, let me go back. This has become tangled. What we want to do is use X bar to estimate mu, and or we want to use S to estimate sigma. We want to use the sample statistic to estimate the population parameter. If the average score of our sample of males who took the SAT in the GRE in 1999 is 824, we want to use that 824 in some way to estimate the average score for all males who took the GRE during that year. In the same way as during elections, any of a number of companies want to use that sample exit poll to estimate the proportion of all voters in that district who voted for a particular candidate. Let's see what we know about the sampling distribution. Let's talk about a specific sampling distribution. Let's talk about a sampling distribution of sample means. A sampling distribution of sample means. That is, let's imagine that we have a population, and let's set sample size equal to 100. We could, would you agree, reach into that population and in an ideal world randomly select 100 of persons from the population and observe those 100 people. And we could get scores for the 100 people, and we could compute a mean and X bar and a standard deviation S. Let's focus on the X bar, the sample mean. Let's suppose that we do that and the first mean score that we compute is 42. Let's call that X bar 1. Now, we could, would you agree, reach into that same population and draw out randomly a second sample of equal size. And we could compute the mean of those scores. Let's call that X bar 2. We could do this a third time. Reach into the population in an ideal way randomly, select out a sample of the same size, compute the average of those scores, and let's call that X bar 3. Theoretically, we could do this, would you agree, an infinite number of times. Theoretically, not practically, theoretically, we could do this an infinite number of times. We could infinitely reach into that same population and randomly select samples of the same size. And we could compute the means of those samples, so that we would have a set of scores going from X bar 1 through to X bar infinity. We would have now a sampling distribution of sample means. A sampling distribution of sample means. Are there any questions? Yes.
When you're repeating getting your sampling mean, like you're getting a new sample out of the population, are the ones that you've already used, the samples you've already used, thrown back into the population?
Yes.
Or so that can,
yes.
like the same person could
yes.
be
The same people will appear in, and so the same scores will appear in multiple groups. Otherwise, this process could not be infinite. You would run out of the population scores. So in the first instance, you reach in randomly, you select out your sample, you take the individual scores of that sample, you compute the mean score of the sample, and then you put the scores back. And then you swirl around and reach in and select out randomly a second sample of equal size, and you repeat the process. And you do this, theoretically, you could do this an infinite number of times. So that the scores you have now are not scores of individuals, they're scores of groups. They're average scores achieved from samples or accrued from samples. So you have a distribution of sample means. In fact, what you have is a sampling distribution of sample means, or a sampling distribution of sample means, if you're from East Texas, or if you're from Katy. If you're from just outside of London, what you have is a sampling distribution of sample means. What do we know about that distribution? Let's first of all go back and add an additional piece of information to the sample distribution and population distribution, and I'll try to do this without erasing or losing everything. The sample distribution is unlikely to be normal. The population distribution may or may not be normal. We talked about attributes in the population that are likely to be distributed normally and attributes that are likely to be distributed in some other way. For example, family income, when we were talking about means and other measures of central tendency. What do you think the mean of the sampling distribution is? Let's imagine you go through an infinite process of selecting out subsets at random, subsets of the same size at random, and computing the mean. You have an infinite number of sample means. What would you think that the average of all of those sample means would be less than the population mean, more than the population mean, somewhere close to the population mean, or the population mean? I'll tell you, it's magic. It's absolute magic. The mean of that infinite number of sample means is mu. So and my writing is so poor because I'm trying to avoid whatever I hit that went. The mean of those infinite number of sample means is mu. That is, the mean of a sampling distribution of sample means equals the population mean. You've got an infinite number of means. Do you think they vary more or less than the population distribution? Let's imagine you've got the population distribution, and let's imagine for the moment that it's normal. You keep selecting randomly from this distribution so that you have an infinite number of sample means. Do you think this sampling distribution of sample means displays more, less, or as much variance as the population? Well, it can't exhibit more variance than the population distribution, because the population distribution constrains the available scores. Even if you select in one of your samples or more than one of your samples all of the extreme scores at the negative end of the distribution, and then all of the negative scores, all of the positive scores at the end of the distribution, the variance, the distribution of scores cannot exceed the base from which those mean scores were selected. So if we have three choices, that the standard deviation of the sampling distribution is either sigma, it's greater than sigma, or it's less than sigma, we can cross out greater than sigma. This sampling distribution of sample means cannot display more variance than the population. What are mean scores? Give me another word for mean. Average. So these sample means are averages. What is the mean of 0, 4, and 8? 4. The variance of that set of scores then is 0 minus, the standard deviation is 0 minus 4 squared, which is 16, plus 4 minus 4, 0 squared, which is still 16, plus 8 minus 4, which is 4 squared, which is 16. So the variance of the set of scores is 32, and let's presume it's a sample, 32 divided by 2, which is 16. If you reach into that population, that group of scores, and select out a sample, the 0 and the 4, the average of those two scores, the mean of those two scores is 2. If you reach in and pull out the 0 and the 8, the mean of those two scores is 4. If you reach in and pull out the 4 and the 6, the mean of those two, the 4 and 8, the mean of those two scores is 6. Yes? Is that distribution more or less or as varied as the original scores? The original scores you had was 0, 4, and 8. the only combinations here, the only possible combinations of two scores are the 0 and the 4, and the average of those is 2, the 0 and the 8, and the average of those two scores is 4, and the 4 and the 8, and the average of those two scores is 6. Is set B more varied than set A, less varied than set A, or as varied as set A? It's less varied than set A. So what we know about the standard deviation or the variance of the sampling distribution is that it is less than sigma. That is, there is less variance in the sampling distribution than in the population distribution. We demonstrated that with this simple example here of comparing a population to a set of sample means drawn from the population. What is even more magical, and I'd really lock yourself down in your seats for this, because this is real magic. The standard deviation of the sampling distribution is equal to sigma divided by the square root of n. Sigma divided by the square root of n. Let me ask you about the shape of this sampling distribution. Is it normal or not? What would you guess? Do you think it might be normal if the population distribution is normal? I got a feeling that I'm like this. And if I look round, I may not see anybody. Don't worry. Let this all wash over you. In the end, you will see the light. You will be healed. Let me go back to the whole notion of sampling for a moment. If the objective of sampling is to use the sample statistic, for example, the sample mean, to estimate the population parameter, the population mean, do you think it's better to use large samples or small samples? Large samples. The more the merrier. Who is going to trust a study of the incidence of breast cancer in women between the ages of 40 and 55 if they only look at 2 women? You may have done before, but having taken this insightful class, I won't say anything about the insightful instructor. This insightful class, you ain't going to believe that anymore. In sampling, the more the merrier. Why? Because the larger the sample, the more reliable and the more valid are the statistics associated with that sample. Let me say that again. You might see it somewhere, who knows? The larger the sample, the more reliable and the more valid are the statistics associated with that sample. That's simply validating your previously common sense realization that all other things being equal, large samples, studies based on large samples, are likely to provide more insight and more information than studies based upon small samples. You know, those 4 who made it into the study may simply be all from one end of the distribution. They may be statistically deviant. When you're dealing with large numbers of people, the deviance at the one end of the distribution are most probably counteracted by the deviants that are selected into the study from the other end of the distribution. So that the sample statistics start to look more like the population parameters. They're more reliable and they're more valid when they're based upon large samples. Let's assume that the population distribution is normal and sample size is large. If the population is normally distributed and sample size is large, what would you say would be the shape of the sampling distribution? What would you say would be the shape of the sampling distribution? Box shape, Mickey Mouse shape, amphibious landing craft shape, normally shaped, if the population is distributed normally and you select repeated samples, repeated large samples of size n, the sampling distribution will be normally distributed. The sample distribution will be normal. Central limit theorem. Central limit theorem. This is a $250,000 idea. What the LA Galaxy should have done is not buy David Beckham. They should have bought the central limit theorem. A lot more return. Doesn't look as cute in a shirt, but who cares? There are other things besides looking cute in a football jersey. Central limit theorem argues that if repeated samples of size n, where n is large, are drawn from the same population, with mean equal to mu, and standard deviation equal to sigma, with mean equal to mu and standard deviation equal to sigma, the sampling distribution of sample means will have a mean equal to mu and a standard deviation equal to sigma over the square root of n. Will have a mean equal to mu and a standard deviation equal to sigma over the square root of n, and will approach normality. And will approach normality. And here is the real magic, comma, even when the population is not distributed normally. Even when the population is not distributed normally. Ideally, at this point, well, I won't talk about the shudder that's passed down your spine, or the hairs that have been raised on the back of your neck, because I know that's happened. But don't you at this point just get the vaguest of glimpses of the significance of sampling distributions? You know a lot about the sample, and you know essentially nothing about the population, but you now know a great deal about the sampling distribution. One key thing that you know is that regardless of the way in which the population scores are distributed, the sampling distribution of sample means will approach normality. It can be treated as if it is a normal distribution. What does that mean? It means all of that stuff we talked about when we talked about the normal curve. It means the mean equals the mode equals the median. It means that the distribution is symmetrical about the mean, but coincidentally, because the mean equals the mode equals the median, in normal distributions are also symmetrical about the mode and symmetrical about the median. We can do all of that those magical little tricks with table A, partitioning off certain areas under the curve. That is a certain specific proportion of all scores in the distribution. We can take a real sample score, X bar, transform it into a standardized Z-score, and put it in that distribution, and talk about it relative to the mean of all scores. What is more, if we have selected our sample randomly, then X bar, the sample mean, is an unbiased estimate of mu, the population mean. If you've selected the sample randomly, X bar, the sample mean, is an unbiased estimate of mu, the population mean. That doesn't mean necessarily that X bar equals mu. It doesn't mean that the sample was some microcosm of the population. It simply means that you can treat, and this is important, that you can treat this unbiased estimate, the sample mean, as if it were equal to the population mean. You can treat the sample as if it were representative of the population. There's a lot of information here. You were aware of sample distributions and sample means and standard deviations before you came in here today. You were aware of population means and population standard deviations before you came in here today. You were aware of normal curves, normal distributions before you came in here today. What you didn't know was issues dealing with, first of all, sampling. Specifically random sampling, which guarantees an equal probability of selection. The payoff from random sampling, or more generally from probability sampling, is that you can treat the sample as if it were representative of the population. That is, you can treat the sample mean and standard deviation, but let's focus on the mean. You can treat the sample mean as if it were an unbiased estimate of mu, as if it was mu, rather, because random sampling defines that estimate as unbiased. You've also learned about sampling distributions, specifically the sampling distribution of sample means. The sampling distribution of sample means is hypothetical. It does not exist in reality. But we know a great deal about it. We know that it has a mean equal to the population mean, mu, as long as sample size is large and the samples are selected randomly. It has a standard deviation that is systematically related to the standard deviation of the population, sigma divided by the square root of n. And you know its shape. The distribution of sample means is normal, even if the population distribution is not normal. Are there any questions? Because this is where I stop cycling. This is where I peel off to have a break. I'm going to get some juice and maybe one of those croissants or something equally French. Maybe a Perrier. Maybe some Camembert or Brie. You, meanwhile, are going to cycle through exam 1. And I'll pick up with you after that. Are there any questions?
If that's true, and the
Hang on. Something might be said that's useful to you.
And the sampling distribution approaches normal even when the population distribution isn't normal, then how do you explain, the curve when it comes to like distribution of wealth and stuff like that? Because it's still not a normal curve.
The population, it doesn't matter. If the population is distributed in a non-normal way, such as the distribution of family income in the US, if you reach into that population of scores an infinite number of times and draw samples randomly, and if sample size is large, the resulting sampling distribution of sample means will be distributed normally. That's you can demonstrate this. This is not some sort of guesswork. You can demonstrate this. But it is nonetheless the case. Okay. We're done. Now, don't run off. We're done, but don't run off. First of all, anybody who did not receive a handout prior to the class meeting, please pick one up before you leave. Second,